Hi everyone, this is Matas from Blue Guardrails. Today I want to show you one approach to detecting hallucinations that is available through Azure. It's called Azure Groundedness detection. And I want to talk you through why it's not sufficient to actually reliably find hallucinations in agents or RAG applications. And I also want to show you how you can self-build a similar approach that is very easy, very cheap to implement, and that gives you a baseline. But same as Azure, it's far from enough to actually handle hallucinations in production. All right, so Azure Groundedness, basically you can put in a task like summarization, Q&A, you put in the grounding sources and the text that was generated by a model, and then you get if it was hallucinated, basically. And I ran this hallucination detection through a subset of the RAG truth benchmark. This isn't exactly RAG truth. We slightly modified it, relabeled some data. We're going to publish that soon, but already it's a much higher quality data set that I can use to test these kinds of approaches. I'm testing on 200 samples of that data set. You might want to scale that up in production. And I prepared a notebook for you to kind of walk you through why Azure Groundedness doesn't cut it. So I have some data set up, and I already ran the groundedness detection. And now I want to show you essentially how Azure benchmarks against the data set. You can see here that we're achieving an F1 score of 0.36, which is really, really bad, honestly. You'd want to be much closer to 1 to actually have a reliable hallucination detection system. You can see that precision is only 0.46, so in half the cases that Azure Groundedness says this span is a hallucination, it's actually a hallucination, and then it only finds like 30% of the actually occurring hallucinations. And if we look into some examples, we can see why that is. I would say essentially Azure Groundedness lacks the reasoning capabilities that are needed to find more complex or slightly more complex hallucinations. So in this case, the task is summarization. And in the original, we're talking about 100 people who caught some illness on a cruise ship. And it was 95 passengers and 5 crew members. And then the model response says it affected 100 passengers and 5 crew members, which is a hallucination as marked here in the ground truth. But Azure actually doesn't find that. Most likely because it's using a small transformer model to find similar spans in the grounding texts, and then there's 100 in it, there's 5 crew members in it, so it doesn't classify this as a hallucination. Next up, we have another example. This time it's about chard, Swiss chard. And in the grounding sources, it said that chard is a subspecies. Let me get the biology right. It's not a subspecies. It's a it's a descendant. It's a descendant of the sea beet, which is in Latin called Beta vulgaris subspecies maritima, so sea beet. And in the model response, the model says chard is this type of sea beet, instead of saying it's a descendant. And if you Google it, you will find that actually chard is not Beta vulgaris subspecies maritima. So that's a hallucination. We have it 2 times in the model response here. But again, Azure Groundedness doesn't find it because It just compares similarities, and then the words are in the grounding sources, so it thinks, okay, that's all right. It's not a hallucination, whereas actually it is. Now, for a third example, this one is about a TV show, and it's kind of summarizing the TV show. Now here, Azure actually finds one hallucination that is very clear because the character here, Eric, has been diagnosed with an illness, but it's not said what illness that is. And here in the model response, the model says it's Alzheimer's disease, which clearly isn't stated anywhere in the text. And then there's another hallucination, and that's more like a subtle logic error, which Azure doesn't find. And this is that RJ, another character in the series, doesn't want to tell Eric about his condition yet. And this makes it sound like RJ is the one who has some disease, but actually it's Eric, as stated in the text. So this is a subtle logic error where the model gets wrong who actually has the disease. And Azure doesn't detect it as hallucination either. So you can see that many things are going wrong. And I try to kind of reverse engineer what's going on, trying to find what kind of model Azure is likely running behind the scenes. So I set out to build a simple hallucination detection method that likely has the same pitfalls and shortcomings, but that helps me reverse engineer what Azure Groundedness is doing. So for this simple hallucination detection, we are using two models, two cross encoders. These are not fine-tuned on the task of detecting hallucinations. They're fine-tuned to re-rank search results after a retrieval step. And they basically detect if two sentences are similar. So if you put two sentences into a cross encoder, like what is the capital of Germany, and then Berlin is the capital of Germany, you get a very high score, in this case, 0.96. Then if I ask what is the capital of Germany, and the answer is the weather in Berlin isn't nice in winter, I get a lower score, in this case, just about 80% similarity. And we can use this model to also benchmark hallucinations by extracting the model response sentence by sentence and then comparing against chunks of the original grounding sources. So what we're doing also is we use two models. That's called using a model ensemble. Typically that improves performance, and I found that it improved F1 score by about 3 points. So I went for two models. The total parameter count of these two models is still only 170 million parameters, meaning they're very fast, they're cheap to run at scale. You can likely even run them on a CPU if you want to. And it's going to cost you next to nothing when compared to proper large language models with a parameter count of 3 billion parameters and up. So what we do here is we have a user message, which essentially are our grounding sources, and then we have an assistant message, which is the model's response. And we tokenize the assistant message into sentences because we're going to do sentence by sentence prediction essentially. And then we use a sliding window of 3 sentences with an overlap of 1 sentence for the grounding sources and split that up as well. And then we run it through our two models and predict a set of scores. And then we take the maximum score. So that's going to be something between 0 and 1. And we store that score with the sentence we just got from the assistant. And yeah, let me run this code real quick. So here we have the models. We have our predictions. That works. of our function. And now we run the predictions, scoring all of our evaluation set using this simple method. And this is scoring 200 user message, assistant message pairs with a few sentences in them each. And it's running that through 2 models as well. So this is going to take about 5 minutes. And I'm just going to go grab a coffee, and then we speed this up and can pick up from there again. All right, predictions are done. I got my coffee. So now we have the assistant sentences, each with a score, or 2 scores actually, one from the first model, which is this one here, an IBM Granite re-ranking model, and one from the second model, which is a cross-encoder based on the MS Marco dataset. And this one is really, really small. Now, we added another step, and this is where we actually customized a model very slightly. We used the setfit library, you can find it here, to train a model that says if a sentence needs verification or not. So especially as you're working with weaker models, like maybe the Llama family of models, and back in 2023 when this benchmark was created, you get sentences like, sure, let me help you with that. Let me know in case there's anything else I can do. And these sentences, of course, they don't need grounding. They're just conversational filler that the model adds to the response. And then we trained the setfit model using just 50 examples per class, so 50 examples with these kinds of sentences, and 50 examples where it's a sentence that actually needs grounding, like citing some facts or figures or something like that. And this training, fine-tuning runs in under 2 minutes on my MacBook. So it's something that anyone can do, even without specialized hardware or anything. And now, now we're predicting using this setfit model. This is about 30 seconds, really fast. And we're adding to each span if it needs verification or not, so that we can later on filter the spans that don't need verification. All right, so this finished. Now let's get to evaluation. We are benchmarking Azure against our simple detection approach. Remember, Azure had 0.36 in F1 score, and you can see here that using our very simple approach that anyone can reproduce at home, we get almost 0.39 in F1. The recall is a little bit higher, the precision is a little bit lower compared to Azure, but overall the score is about 2.5, 3 points above the Azure Groundedness detection. Now, if we look at this, in the examples, we can see that this approach has the same shortcomings. So 100 passengers and 5 crew members, our approach doesn't find it because it cannot reason. It just uses similarity, probably like Azure Groundedness does as well. For our chart, it finds one hallucination, but doesn't find the other one. So it's slightly better than Azure, which we can also see in our metrics. And then we have the third example where all approaches find the clear hallucination, the Alzheimer's disease, but both methods fail to detect that RJ isn't actually the one who's sick, but Eric is. So as you can see, it's very simple to build these small encoder model-based hallucination detectors. Try it out if you want to. This code is very simple. to reproduce. But again, they're not sufficient to evaluate real-world hallucinations. And this is also why using Azure Groundedness can give you an idea, but it can't really protect your system from hallucinating in critical circumstances. All right, that's it. We're going to share more of this stuff, so tune in again. And thanks for listening. Bye.